In the preceding tutorial, we have discussed the various methods of generating singulate oxygen from its ground state, the triplet oxygen molecule. And of course, it's somehow surprising that the diradical should be lower in energy, being less reactive. Some kind of stabilization must take place here. We know that from our all-day experience, since combustion always needs some activation energy. In the case of hydrogenation, the first equivalent of hydrogenation leading to hydrogen peroxide will deliver 32 kcal per mole. The second equivalent, then leading to the final product, water, delivers 115 kcal per mole. So, some stabilization is taking place here, and it's a mesomeric stabilization. Let us remember typical examples of mesomeric stabilization, for instance, aromatic systems. A benzene ring with two mesomeric structures. The truth lies in between. Since all bonds have the same length, we can put those mesomeric structures into brackets and draw it like this with the aromatic sextet in the center. Or the allylic cation with one and the second mesomeric structure, we can draw that as a delocalized allylic cation like this. To visualize the mesomeric stabilization of the oxygen diradical, we should assume having an sp hybridized molecule. That means at both oxygen atoms, two p-orbitals will remain, one completely occupied, the other one with the radical electron. We have to take into account the geometry. The fully occupied p-orbital is perpendicular to the one at the other oxygen, simply because of the electronic repulsion of the negative charge. So, taking into account the geometry of a molecule, there is another mesomeric structure here, where the vertical fully occupied p-orbital is in the oxygen behind the whiteboard, and here it was at the oxygen in front. Which other mesomeric structures do we have? Well, ionic ones, dipolar ones, with both fully occupied p-orbitals at one oxygen, and that means we have here a negative charge, there the positive, and here it is the opposite, positive charge there, negative charge there. Since the truth is again in between, there is overall no dipole moment resulting for the oxygen diradical. And this mesomeric stabilization is also responsible for the fact that the O2 diradical does not combine, for instance, to an O6 ring or an O8 ring, while the S2 molecule, we all know, is stabilized by the formation of a ring system with 8 sulfurs. Thanks for listening.